Hello, students. We are into the last section of our first chunk. So the first chunk was about algebraic thinking. I've tried to tie in a lot of concepts we've seen previously in Math 105 to illustrate that they still exist. They're still important to know. And I want to take this opportunity to go back to something like addition and subtraction. So this concept of addition and subtraction we've seen in different number bases. And what we're going to see now is very similar to maybe parts of that, but what we're going to see is some connections that make it able to be expanded. Okay, so we'll take a look at those. The concept here is very similar to what you might see on a clock. And for some students in elementary, early middle school, they would be like, okay, reading a clock is one of those skills that is still somewhat needed, although recently, with most people having a cell phone in their pocket, that is not quite as critical. But the old hands of a clock situation allows for opportunities like this. So in a traditional clock, right, we have 12 up top, 1, 2, 3 to the side, 4, 5, 6 at the bottom, 7, 8, 9 on the other side, and 10 and 11 that direction. That seems a little bit like a heavy line there, so I may change that as I go. So again, if something happens at 6 o'clock, the hour hand would be pointing down to the 6. The minute hand would be pointing up, but the hour hand is kind of what we're referring to. So then if we went from 6 to 9, we'd add 3 hours. So again, 6 plus 3 giving you 9. That really doesn't seem like that big of a change, right? 6 plus 3 gives you 9. Then you say, well, I'm going to add another 3 hours. Okay, well, that gets you to 12. Now you're at 12 o'clock. And if we say we add 3 hours, in your mind, 12 plus 3 should be 15 over here, but we only record it as 3. So that means we have to be a little careful. So again, in the past, 12 plus 3, we'd say 15. Now that we're dealing with this in what we would maybe consider a clock situation, we don't want to use the same symbols. And so let me go just a little bit thicker than that, and I'll show what I mean. What we're going to do now is we're going to say 12 plus, and because this addition is different, we're going to put a circle around it. And we're going to say it this way. So we're going to say 12 plus 3, and that means we're thinking about it on a clock. 12 plus 3 hours gets you to 3 o'clock. Okay. For example, 11 plus 4 traditionally would give you 15, but on a clock, especially at 12 o'clock, 11 plus 4 is going to get you where? Start at 11 and count forward 1, 2, 3, 4. That gets you to 3 o'clock. Okay. All right. So that's the idea. That's why when you see this arithmetic, it's going to look a little bit different, but the meaning is pretty similar. We're still adding things. We're just treating it as kind of it loops around. And so that is the idea of a 12 clock. Now, when you see things, you'll see some things that really look a little strange, but once you understand it's on the 12 clock, you're like, oh, actually, that does make sense. If it's 8 p.m. and I add 12 hours, guess what? It's still 8 o'clock. It's just from a.m. to p.m. So we're not indicating a.m. and p.m. because most clocks like this do not indicate that. So we just kind of think of it kind of going around in a circle. Yes, if you were in the military, you might have a 24-hour clock. That's possible, but we're going to stick here with a 12 clock. Although we could do other clocks, like we could come up here and make a 6 clock. So if it was a 6 clock, I'd have a 6 up here on top instead of a 12, right? And then a 1, 2, 3, 4, 5. So these are the only numbers I can ever get. So then if I say something like, okay, well, what is 5 plus 3 in a 6 clock? You can come up and kind of count forward and say, okay, so 5, get me to 6, 1, 3. Okay, so 5 plus 1, 2, 3. Okay, it's 2 o'clock. Okay, absolutely. 100%. But again, that's just because if you think traditionally 5 plus 3 would give me 8, but 8 is bigger than 6. So in a sense, we're regrouping. Again, I wanted to tie this back into the number basis. We can think of it as regrouping. So we pull off a 6, and we pull off a 6. That means there are 2 remaining. Okay. So that can be kind of the way that you think about that. Okay, so let's talk about arithmetic on a clock. So when we talk about arithmetic on a clock, we can do all the same things. We can do 1 plus 1, 2 plus 2, 3 plus 5, all of those. We can even make a table for it, like is listed here. So this is addition, and you'll see this addition right up over here. And honestly, if I were them, I would have written addition with the circle around it. So I want you to think about this. This is not traditional addition. Why not? Well, I mean, 12 plus 12 turns out to be 12, right? So that right away indicates something different. 12 plus 1 is 1, 12 plus 2 is 2, 12 plus 3 is, and so on and so forth. 1 plus 1 is 2. So again, you get some numbers that you're kind of used to, but almost once we hit that 12, right? Remember, then it's going to kind of regroup. So this all looks very traditional, but after that, then you can come down and say, well, 8 plus 7, that gives me a 3. Normally, I'd think 8 plus 7 would be 15. Okay. So again, now there are some properties that we've seen in the past that do exist here. So let's see if we can kind of spot those. Addition was a concept that we have pretty well done. So do we have commutative property? Well, let's see. If we have commutative property, then 3 plus 2 should be the same as 2 plus 3. Well, let's check. 2 plus 3 gives me there. 3 plus 2 gets me there. And they're both 5. Okay, so that makes sense. Now, visually in this table, if you're looking for the commutative property, because the order doesn't matter, you should be able to see symmetry. And that symmetry should be right down this line. The diagonal goes all the way through. So if you can kind of flip the table over and the entries match, then you're good. You have the commutative property holding. So let's see here, 9 plus 5. And if I connect that over here to 5 plus 9, so what you can see is this kind of reflective symmetry. Both of those give you a 2. So again, that's kind of an indicator that we're on the right track. 10 plus 1 should be the same as 1 plus 10. So those again connect and they kind of reflect across each other. And I'm looking at this, and again, if I was the one who had built this table, I probably would have made them squares instead of rectangles. Making them rectangles means that it looks like it's a little off when you kind of flip things over. If you had made them squares, it would have been perfectly on, but not my book to write. All right, the identity property of addition. Okay, let's think. Identity property. Ooh, is there a number that I can add and stay with the value I had initially? So again, with traditional addition, we would say 3. We add 0, we get back to 3, and 0 is our identity element. And yes, there's always a number, 0, that we can add and stay the same as we started. Do we have that with this 12 clock? Is there a number I can add to anything at all? So be thinking, what can I add to the number 5 to get back to the number 5? Oh, and by the way, because of the commutative property, you could also write it this way. Okay, is there a number that I could use to fill in that cloud? That would be the identity property. Okay, and then the inverse property. Okay, this is going to be great, right? The inverse property. Okay, so whatever your identity is, and let's see here. Hopefully you can spot it here. What is my identity? Okay, so if I look in the addition table for 2, if I ever see a number 2 in here, that's like a trigger. Okay, 2 plus 12. So if I check the 5 column, 5 plus 12 gets me to 5. So this is a little tip off right here, right? This tells you the number you're looking for is 12. In a 12 clock, 12 is your magic number. Okay. So 12 is the identity element. So it does work. Okay. Now the question is then, is there an inverse property? Okay, now we saw this first time in chapter 5 when we were dealing with integers. But is there an inverse property? Now let's think about what that means. It does involve the identity element. So if I take the number 5, you have to ask yourself, what can I add to get back to the identity element? Little asterisk there. Okay. In the past, historically, oh, and I should say this is addition with the circle around it. That's what I should say. And I should say this is addition with the circle around it too. I gotta be careful. The original one was regular addition. So if we go back to regular addition, 5 plus what number got me back to 0? And you remember this was in chapter 5 because it was the first opportunity we had with negative numbers. So the additive inverse was -5. Well, look in this table. We don't have negatives. Sorry about that. We do not have negatives. But is there still a number that I could add to 5 to get to the identity? And again, the identity is 12. So in this case, it's not, you're like, oh, well, actually, I think then it should be just 7. 5 plus 7 is 12. And you're absolutely right. So if you think about that, that's exactly how we would go through and find the additive inverse. So there is always an additive inverse, and you can tell that because we have a line here of 12s. Every single number has a 12. And so that means anytime you find a number, you can add something to get back to the additive inverse. And you could also see that picture-wise. So with the symmetry of the 12 clock, let me just erase these and then move up just a little bit. So if you think about the symmetry of the 12 clock, your inverses, right? So if you think about the number 5, here's 5. That is a really big, why is that so? Okay, let me try that again. Let's try that again. Oh, there we go. That's a little bit better. Here's the 5, right? The inverse of 5 turned out to be 7. So if you take a look, 7 is right here. The inverse of 2 turns out to be 10. And so you can kind of see on this clock, wherever it is, if you think of just counting, like if I go this direction, you can almost think of this like a number line. I go up to +2. To get backwards, I'd have to go backwards 2. And if you count backwards 2 from 12, which is like 0, then you're going to get to 10. So that's how you can kind of visualize the inverses here. Yeah, so pretty cool. Pretty cool. Let's see here. We allow those. So we could also do addition and subtraction and so forth. But we're going to just kind of start with addition. What does that mean? It means we also have subtraction. We do have subtraction, and subtraction up here would be like a couple different things you could do, but let's take a look. You can think of subtraction as kind of your traditional, the idea of 5, and I take away 3 on a clock. If it's 5 o'clock and you go 3 hours before that, you get 2 o'clock. Okay. But why? Come down and check it. Well, because 3 plus 2 gets me to 5. And if you want to check 3 plus 2, it gets you to 5. What's another way to do that? Well, what we saw previously is we had subtraction. So this goes back to chapter 5, that subtracting the opposite of a number, or adding the opposite of a number, was the same as subtraction. And we had to prove it back then. But we could do that. So this is the additive inverse. So we actually could do the same thing. So what you have to do is think, in a 12 clock, what is the additive inverse of 3? So instead of actually doing subtraction, we could rewrite this as plus 9. Because subtracting 3 is the same as adding the opposite. The opposite is 9, because 9 plus 3 is 12. So 9 plus 5 is 14. 14 in a 12 clock means I went 2 past. So I would say 14, which we know is equal to to 2. I don't know why I wrote 12, is 2. So I get the same answer doing it that way. The reason is there's going to be times where, because we have to answer with a number between 1 and 12, doing something like 5 take away 7. So now it's 5 p.m. What happened? What time was it 7 hours ago? We have to go back in time a little bit. So there's a couple ways we can do that. One is to say, turn this into the additive inverse, right? So we would say, oh, well, the additive inverse of 7 is 5. 5 plus 5 is 10, and we're done. We could use the table to find, right? I want 7. So I'm going to go right here, find 7, because that's what I'm subtracting. And I say, when do I get to 5? Go all the way across till you get to 5. And they'd say, oh, there's my number. It must have been 10. Okay. What's another approach? Add the inverse. Nailed it. We could temporarily rewrite this as the same equation, but then just add 12 hours onto anything. Remember, 12 hours plus 5 gets you the same value. So now just add 12 to the 5 and you've got 17 minus 7. Maybe that's quicker for you to see that it's 10 o'clock. So there's a couple ways that you can go about doing this if you want. Other people have said, well, wait, Scott, could I split that up? What if I know I need to take away 7, but couldn't I just take away 5 to start? And that gets me back to 12 and then take away the other 2? Absolutely. 100%. So a lot of different ways we could go about doing subtraction. But again, subtraction is going to be that unique number that I add to get to my value. So again, let's see here. They do have multiplication. They do multiplication. So 3 with a clock times 5, that's the clock piece, would be 5 plus 5 plus 5. Now you know that's 15, but in a 12 clock, we have to kind of remove anything bigger than 12. And so just take off 12 at the end and you get to 3. Okay. So there you go. So that's it. So yeah. So multiplication, addition, subtraction, they all kind of stay the same. We just have to remember we're in a clock. Oh, I guess yeah, I was just thinking about that subtraction where I had 5 clock subtract 7. You know what? In your mind, you actually could think of this as -2, right? It's -2, but where is -2 if this was like a number line? And on the clock, you remember it went 1, 2, 3, right? So if you're counting backwards from 3, 2, 1, 12 is kind of like 0. And so you'd count backwards to 11, which is like -1, and 10, which is like -2. And you could get to the answer and say, ah, it's 10 because it's 2 before the 12. Okay, so you could actually think of having negative numbers. We just wouldn't write them as our final answer. And there we go. Phew. So again, the book does talk about this as counting backwards, counterclockwise, but why not use what we already know? So they're going to ask you to do some computations on the 12 clock. You could do these on any clock. Okay, really you could. So maybe I will ask you to do them on a 7 clock. So if I said, what is 6 plus 6 on a 7 clock, then you would say, okay, well, 6 plus 6 is 12, but on a 7 clock, I got to pull out all my 7s, which means my final answer is 5. Okay, that's it. You could also look at the clock and say, wait a minute, but 6, that's 1 before 7. So this problem actually is the same as 6 plus -1. And 6 plus -1 is 5. Yep. And you can actually do that with our 12 clock. So if you think about 11, you want to add 11 hours, right? Then 11 is the same as -1. So if it's 8 o'clock now and you want to add 11 hours, right? In your mind, you could say it's 19 o'clock, but you could also say, wait a minute, going forward 11 is like going forward 12 and then taking 1 away. So really that becomes exactly the same as 8 minus 1. And so you'd be at 7. If you went the other way and you got 19, just take off your 12s and you'll get to 7 as well. A lot of cool stuff can happen here on this clock then. Okay, so a couple sample problems here. They have things like 4 minus 12. But again, 4 minus 12. 12 is my identity. It's like 0. So 4, take away 12 hours, it's 4. Okay, that's it. Yeah. A 4 minus 4? Don't beat yourself up. 4 minus 4 is like 0. But again, 0 is acting like a little bit of a different number now. On a 12 clock, we don't have a 0. We would call it 12. Yeah. So 4 minus 8, again, I can think about I can do what is the additive inverse of 8 if I want. So I could say 4 minus 8. Okay, well, that would be the same as 4 plus 4, which gets me to 8. Or I could have said 4 minus 8 is equal to negative 4. And now I just need to think what's 4 hours before 0 or 12. And the answer is 8. Okay. All right. Now let's get down to division here because division is going to be crazy, crazy, crazy on you. Do, 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 do. All right, let's see here. So I need to do this piece. Now, you know what? I actually think, I think I need to open up a sheet to make a multiplication table. I think a multiplication table would help. If you're just learning these pieces, the multiplication table is probably going to be the easiest thing. But um, um, I think it might be helpful because in this case, when you do 3 divided by 2 or 2 divided by 7, you have to think of what multiplies by 7 to get me a number. So instead of doing the whole table, what I'll encourage you to do is if you want, if you're doing a bunch of questions on a 12 clock, build the table. If you're doing just a couple questions on a 12 clock, it's probably fine to just do a single row of the table. And let me show you what that would look like. So let's say that we want to do, okay, 3 times 11, I'm not going to stress, that's 33. And then I take off my 12. So take off 12, that gets me to 21. Take off 12, that gets me to 9. Okay, so I'd say 9 o'clock. And then 2 divided by 7. So that's a trickier one, right? Because 2 divided by 7 on a clock is some number as long as 7 on a clock multiplied by that number gets me to 2. And that's the hard thing, right? 7 times what has a remainder of 2? So it's a little tricky there. So let's try this. So what I'm going to do is I'm going to multiply by 7. 7 times what, right? So 7 times 12, 12 is like 0, okay, gets you to 12. It acts like 0. Okay, this is multiplication. 7 times 1 is 7. 7 times 2 is what? 7 times 2 is 14. Okay, so 14, but on a 12 clock would be 2. 7 times 3 is 21, but on a 12 clock, that's 9. 7 times 4 is, excuse me, 7 times 4 is 28, but I take away 12. I take away 12. That's 24. That gets me back to 4. And here's where I want to kind of say there might be a quicker way than actually doing the multiplication. You notice what's happening. In my mind, I'm getting up to bigger and bigger numbers and having to take off groups of 12. I want you to see this. If you went, and remember multiplication is like repeated addition, at least for what we're doing. So this is like 0. And if I go and add one more group of 7, I go up 7. If I go add a group of 7, that gets me to 14. I have to take off 12, gets me to 2. If I add a group of 7, that's 9. If I add a group of 7, that becomes 16, but I take off 12 is 4. If I get to the next number, adding 7 would just be 11. Adding 7 looks like 18, take off 12. Do you see what I'm doing? All I'm doing is adding 7s, so it doesn't make it so I have to really like do the multiplication. That should be a 10. And then 11. So I'm not doing the multiplication anymore. Yes, I could do 7 times 7. That's 49. And then I need to take off a bunch of 12s. I don't want to do that. So what I do is I just add 7 as I go. 7 plus 6 is 13. Take off a 12. Add 7. Add 7. 15. Take off a 12. Add 7. Add 7. That's 17. Take off a 12. And what I can see is I've got every possible number here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is a multiplication table. So if somebody said do 2 divided by 7, I'd need to find what do I multiply by 7 to get 2. Okay. Now the book chose this question. Thinking if I was with the author, I'd been like, why the freaking A did you choose that question? I still don't understand. Well, that's fine. So you look at your table, 7 times what gets me to 2. So I find the 2, again, which is my final answer to, and I say what got me there. The answer turned out to be 2, which again is not the best one as your first example in this, but let's do a couple more so you can understand why I think that's not the best idea. Okay, does that make sense? So here we go. So there we are. So 2 is the answer because 2 times 7 gets me to 2 as an answer. Let's try one that actually probably is going to make a little bit more sense. All right, let's come down and do this. I would not have asked that question, at least not as my first one. Maybe down the road, but I probably would have said, let's do 3. Let's do 3 and divide by 7. Okay, so now you're looking for some number. That's going to be your answer, as long as 7 times that number gets you to 3. So now look in the answers up here, and you got to find where is 7, find 7, and go across until you get a 3 as an output. Okay, so come up here, bingo. There's 3 as an output. What number got me there? 9. So 7 times 9 is 3, which means 3 divided by 7 is 9. Okay, so there we go. We've got it. Not only that, not only did we find an answer, but the answer is unique. That was one of the key conditions on division. It had to be unique. So that's what we looked at here. We found a nice way of making that unique. Okay. Phew. So there we go. That's division. Okay. All right, let's see here. What else could we do with this? Okay, so you could do anything. This is a times 7 piece. This is like multiplying by 7, which means I would be able to find all divisions by 7 using this one row. Okay. If I wanted to divide by 5, I could not use this row. I'd have to get a different multiplication component going, which means if we want to divide by 2, we are going to need to make a different looking chart. And you get to see something here that may not have happened in the first one. Okay, so now I'm going to do 2. I'm going to do multiplication. So 2 times 12, we know that's going to be 12. Okay, 2 times 1. So again, I can think of multiplying and doing all the work, or I can just add 2 because that's there we go. There's all the things I need to form a multiplication pattern with 2. Okay, so 2 times 1 is 2. 2 times 2 is 4. But again, I can get there by just adding 6, 8, 10, and there's a 12. Now we get to 7 times 2, which again, we could do the multiplication, 14, take off a group of 12, or we could just add 2. I'm just going to add 2 because I don't have to go back through and redo everything. Okay, there it is. All right, so now here comes the fun. Let's go down and do this problem. This problem says we want to do 3 divided by 2, but on a clock. So my answer is going to be some number as long as 2 multiplied by that number gets me to 3. So you find 2 times, this is the 2 times table, and you look across your answers until you find 3 as an answer. And we have a pretty serious problem here. There is no 3 as an answer. Remember, there's 2 things that have to happen with division. It has to exist as a solution, and then it has to be a unique solution. Let's take a look here. So we would say here, there is no solution. So we would call this undefined, just like we would with division. Okay. All right, so that failed. Let's try another one. What if I pick a number that isn't here? Aha, here we go. 6. And I say, what is 6 divided by 2 in a clock? And you would say, no problem. Well, 6 divided by 2 is some answer as long as 2 times that value gets me to 6. Well, let's look through and find it. Some of you are like, I already know the answer, Scott. Thank you very much. I already got this one. So you look across and you say, aha, got it. Bingo. I know that I can look up and find it, and I know the answer is 3. And 2 times 3 gives me 6. Thank you very much, Scott. I've enjoyed the time I've had with you. I nailed this one. And I would say, hold up just 1 second. Because there's another 6 as an output. So what's interesting now is we could actually say 2 times 9 also gives me 6. So the question is, what answer do you put in this box? Do you put a 3 or do you put a 9? And you'd have to write undefined. The reason it's undefined is there needs to be a unique answer, which means it has to exist and it has to be unique, so there can only be one. So in the first case over here, there were no solutions. Doesn't work. On the right-hand side, we have too many solutions. Doesn't work. So division only works when there's a single value that you can use. So over here, sadly, too many solutions. That's why it fails. So there is no answer you can put in there because there's too many options to choose from. There we go. All right, so as you go forward, keep those definitions in mind. Those are back from Math 105 if you're looking for those. The definition of division being unique, having one and only one answer would start in chapter 3 if you need to review that. Okay, so we could come down and do a 5 clock. Now, a 5 clock is very similar to a 12 clock. It's just the 5 is acting like a 0. In a 12 clock, the 12 is acting like a 0. Okay, so moving forward, you can take a look. They've made an addition and a multiplication table for you already, which means you can now do subtraction or division very quickly. So if you want to take a look, what you're looking for to see, can I do division? Can I do these pieces? Is you're looking across a row like this, and you would look and say, in multiplication, do I see every possible number? A 1, a 2, a 3, a 4, and a 5. And if you do, then that tells you that you do have an inverse. Okay. The inverse, multiplication-wise, is what you would actually get when you multiply by, I'm going to choose a different color, multiply to get 1. So the number 1 is our identity in multiplication. And so here I could see 3 times 2 is 1. And since it is 1, I could actually do what we did previously with other number systems. I could do that here. Let me show you what I'm talking about. So if I wanted to do 5 divided by 2, right? I could think, what do I multiply by 2 to get 5? I could do that. Right? Actually, I don't want. I'm going to change that up a little bit. I'm going to change that up just a little bit. I'm going to do 2 divided by 3. Okay, yeah, that's what I want to do. 2 divided by 3. So what that means is I would look and say 2 divided by 3. What do I multiply by 3 to get the number 2? What would I multiply by 3 to get the number 2? I could come down and say, oh, I have to multiply by 4. So the answer here would be 4. You could also come back and say that you could rewrite the problem. Division is the same as multiplying by the reciprocal, and the reciprocal is the number that gets you to 1. So if I look at 3, what do I multiply that gets me to 1? And the answer is 2. So you could actually turn this problem into 2 times 2, and you're going to get the same result. Yes, that is pretty cool. So again, in the past, if we had like 12 and we said divided by 3, just normal, we would have said that's the same as 12 multiplied by 1/3. We get the same result from both of those. The reason that works is 3 times 1/3 is 1, which is our multiplicative identity. Down here, it doesn't maybe look the same, but 3 times 2 is our multiplicative identity. 3 times 2 is 6. Now, if I take off my 5, I get 201. Very cool. Very cool stuff. You can do this on any clock. Now, the idea of clocks leads us to this idea of what is known as modular arithmetic. And the idea of modular arithmetic is that instead of thinking of a 12 clock as having a 12, we replace the 12 with a 0 and everything else stays the same. Okay. So we can find numbers that are kind of in the same position, and we usually write the smallest positive value. So on that 12 clock that we were talking about before, we have a 12, then a 1, a 2, a 3, a 4, a 5, and a 6. When you go around and add 12 to it, you get the next number here would be 13, then 14, then 15, then 16. So what we say is that 13 and 1 are congruent. They're not the same because they're technically different, but they're congruent mod 12. Okay, so we would write this: 13 is congruent to 1 mod 12. So what we're saying is on a 12 clock, 13 hours is the same as 1 hour. Okay, but think about it. We could keep going around then, couldn't we? Because if I go around another 12 times, that would be now 25. So we could say 25 is congruent to 13, which is congruent to 1 mod 12. Absolutely. Okay. And you could go the other direction. So go backwards. This would be the same as negative 11 because I went back 12. So negative 11 is congruent to 1 mod 12. And what I love about this is any time that I'm doing a problem, I can replace it by values that are congruent. So if the numbers are too big, like here, if I was multiplying by 23, but I'm in a mod 4 situation on a 4 clock, I can say 23 is the same as 3. Let me just multiply by 3 because that's a little bit easier for me. All right. So that's how we can use this. And it does make it really nice. If you want to know a shortcut to determining whether they're the same, remember they have to be off by a difference of whatever your mod is, whatever your 12 is. So the difference between these two had better be a multiple of that base. Another way to say that is 12, which is our value, our mod, has to divide the difference between two numbers. And I'll write that here. Okay. So if you want to check, this is mod 10. Find the difference. 23 minus 3 is 20. Does 10 go into 20? Yes. Okay. Let's see here. Look at the next one. 23 with 3 mod 7. Well, 23 minus 3 is 20. Does 7 divide 20? Question mark. And you would say that is false. So we would also say, you just say it's not congruent. Same thing as kind of saying false. Okay. There we go. Next up, find all integers such that x is congruent to 1 mod 10. Now this is where I want to tie this back in because I think you're really going to like this piece. When we do division, because in this case, we're kind of dividing out all the 10s, and we're left with a particular number, that number was the remainder. Here, what we're saying is, what are all integers that have a remainder of 1 when you divide by 10? Now, you can see that by just starting at 1 and adding 10 to find other numbers that are similar. You are creating an arithmetic sequence of all of these numbers that are actually congruent. So if you said, let's see here, if I want all the numbers that are congruent to 3 mod 5. Okay, well, that means, so 3 is fine because 3 is congruent to itself. And then mod 5 means I'd go up by 5 every time. And what you'll notice is I create a nice arithmetic sequence of these. But I could also go the other direction, something we typically didn't do with arithmetic sequences. I could remove 5 and get some negative numbers as well. So there's infinitely many solutions here. You can write them as a set like this, and you have sequences, and you're off and running. Now you'll notice they do write it out. They say, well, wait a minute, if I want 1 left over, so up here, let me kind of show what that would look like here. That means my number x has to be some multiple of 5 plus 3, because I have to have 3 left over. So this gets us back to the division algorithm from chapter 3. So again, good connections. As you can see, there's a reason why. We're going to need this when we get into the reason why I'm doing it now, and I didn't do it back then. I know this was linked to chapter 4, is back then we were already fighting with a lot of concepts, and I felt like adding one more probably would have pushed some of you over the edge. So what I'm doing now is I'm coming back and saying, let's link back to it now that we feel more comfortable with things like fractions, with things like integers, and we've got a really good foundation under us. Plus, when we get to angles, which is coming up very soon when we do geometry, as we measure angles, they're measured from 0 to 360 degrees. 360 is like going around in a full circle. Once you get past 360 degrees, you can kind of say, well, wait a minute, 361 degrees turning around would be just like going 1 degree. I'd end in the same place. So we have a way of using the modular arithmetic with what we're going to be doing going forward. Okay. You could also do it on days of the week. Days of the week repeat, right? It goes Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and then it repeats with Monday, which means it's like it's on a 7 clock. Every 7 days, you're back to 0. Every 7 days, you're back to 0. So if you know something, like in this case, you sign the note on a Monday and it's due in 90 days, then you could just say, well, wait a minute, where is 90 is congruent to what? Mod 7, because we're grouping with 7s. Go ahead and do the division. Take off a whole bunch of 7s. And let's see here. Like I could take off 70. That gives me 20. And I can take off another 14. And that gives me 6. So the remainder is 6. So 90 is congruent to 6 mod 7. So if it starts it on a Monday, you got to go forward 6 days to find out when it's going to be due. Okay. Now here comes the fun for me, right? I said this is fun, or at least I really find this fun, and I hope my enthusiasm rubs off on you. But when you see something like this with a 6, right, you could say 6 is equivalent to -1. So instead of going forward 6 days, just go back 1 day. So if it's a Monday, back a day, Sunday. And again, you can go forward and say it's 12 weeks and 6 days from here, and you got to count forward 6 days. But instead, you could just go back 1. And again, for me, I tend to find that to be a little bit easier for me. Okay. Let's see here. It's Monday, October 14th. On what day of the week will October 14th fall if next year is not a leap year? Okay, so this is one you could use if you want to find out what day of the week is your birthday on next year, if you wanted to. So again, we have 365 days in a year, right? But we're doing days of the week, so we want to work mod 7. So we want to find it congruent to something mod 7. So figure out, take a whole bunch of 7s out of here. And I'm just going to do what we've done before and just pull out a whole big chunk of them, like 350, and that leaves me 15. And then pull out the 14, it leaves me with 1. So guess what? 365 is congruent to 1. So if it's a Monday this year and you go 365 days till next year, your birthday next year will be on a Tuesday because it's just 1 day forward. If Christmas falls on a Thursday, what day of the week will it land on if next year is a leap year? Okay, so if it is a leap year, it's not 365, it's 366. But here comes the fun. If you add 1, just add 1 again. So 366 is congruent to 2. So if it's on a Thursday this year, you just go forward 2 days. So Friday, Saturday, and there you go. It'll be on a Saturday next year. So again, modular math can come in really handy. What's great is I don't care about how many times I go. Right? To me, it doesn't matter how many weeks it is. I just need to know the day. So I don't have to go through a bunch of those pieces. Okay. All right, so you're going to be doing stuff with a 5 clock. I'm going to ask you to create a 9 clock, like addition, multiplication on a 9 clock. There's a 5 clock. Um, just remember that you have to be able to do the operation. And there is a nice little, I'll give you this tip because I know the book didn't push it, but I got to because I think it's important. When you are doing operations on either a 12 clock or in like mod 12 or anything like that, you have to realize that the operation has to be defined. And if your value, like when we were doing division by 2, 2 on a 12 clock had a common divisor of 2. And we noticed that it failed. We could not divide by 2. It either didn't exist or there were too many possibilities. But we could divide by 7. The GCD of 7 and 12 is 1. And this worked. So in order for you to be able to divide on any, like by any number on any clock, the GCD of your number and the mod, which is like your clock number, has to be 1. If it's not 1, you can't do division on that. You can't. There's too many answers or there's not enough. So if you want it to work, you have to be able to do the GCD equal to 1. And that's why when I get down here, like in 1 divided by 3, 1 divided by 3, I check 3 and 12. What's the GCD of 3 and 12? Well, GCD of 3 and 12 is 3. Guess what? You're not going to be able to divide that. I guarantee it. It's either going to be too few or too many, but it's not going to happen. So when they say if possible, you now know that one is not possible. Some of the homework questions are about if this day falls here and it's a leap year. What are the dates of the other Tuesdays in April? Well, what do we have? We have leap year ones. We have non-leap year ones. If you know that it's a 23rd, when are the other Tuesdays? The other Tuesdays are 7 days away. So if you add 7 up and down, you'll find all the other Tuesdays. Arithmetic sequences. There we go. And yes, you could use it here. Isn't this great? If you want to go 101 letters in the pattern, you can see what these are, right? After 5, you can see it's groups of 5. So why not just say, well, let me just get rid of that. Who cares about that? So I go through and I write a whole bunch of these down, right? Let's say what I don't want to do 101st. I'll leave that for you because I think it's in the homework. Maybe I'll say, what is the 347th letter, right? You're like, okay, thanks a lot for that. But it's not a big deal. You know, these are chunks of 5, which means it repeats every 5. So you could just divide this by 5 and see what the remainder is. So pull off a bunch of these and you'll be able to say, oh, well, that's like 345, which is groups of 5 with 2 left over. I'd be like, yeah, that'll work. Yeah. So I go 2 left over, which means I write down 345 clock, and then I go forward 2. 1, 2. Got it. It's an L. Okay. The other one, so sometimes you can look at this and you can see it's really close to 5. You could also say, hey, wait, if you added 3, you'd get to 350, which is a multiple of 5. So you could also count back 3, right? So from the full, you could count back and get there as well. That's totally fine. So there you go. So many different ways to do it. So you'd be here and you go back 1, 2, 3. You also get an L. Totally fine. All right. So what are other things that work kind of like this on a modular piece? Seconds. Every 60 seconds, it rolls over to a minute, but your seconds on your stopwatch, they only go from 0 to 60. Then it rolls over to the minute. So really, when you're looking at that, you could say if I add 45 seconds onto something, what do I end up with? And you could use the ideas we've covered. So 45 seconds plus, and I was at 27 seconds. You can be like, okay, got it. You would know you could add that together and get 60, 72, but 72 isn't going to show up on your stopwatch. They would remove that and say there's 12 seconds that you have. You could also say, because it's mod 60 in a sense, that you could find the additive inverse, which is negative 15. Negative 15 plus 27 is like 27 minus 15. And guess what? It gets you to 12. So you get a lot of power with these, a lot of fun that comes from them. And one of the activities we're going to do in class is actually a code breaking. So using these to encrypt and decrypt certain numbers makes for kind of a really fun activity for kids, as they can send secret messages and somebody else has to try to break those. Okay. A few questions that I'll go through in the next video, and we'll kind of see what we end up with. So hopefully you enjoy this as much as I do, and we'll talk to you soon. All right, off you go.